Yes, hello friends. So this is the video tutorial for today's GFG problem of the day, which is quite an interesting one. It's still continuing on the binary search pattern. So yeah, a lot of time the problem of the day follows a pattern or a topic. Right now on GFG, there's a lot of problems on binary search. So that's the hint for this question. If you did not try this, you should try this, and yeah, you now also know the hint of binary search. Yeah, the question says that you're given two sorted arrays A and B and an element X. The task is to find the element what that would be at the kth position of the combined sorted array. So we can use this test case to explain what the question asks us. Okay, I already had this opened here. Yeah. So for this test case, the k is 5, right? So if I say that k is 5, so I need the fifth value. So this is a sorted array and this is a sorted array. I need to combine these both sorted arrays. If I combine both of these sorted array and get a sorted array, another one, the final sorted array, the combination of this and this would be 1, 2, 3, 4, 6, 7, 8, 9, 10, right? This array. Now I need the fifth value of this, right? So the fifth value, this would be the first value, second value, third value, fourth value, and fifth value. So the fifth value is 6, and 6 would be the answer for this test case. Now, one way that you could suggest me to solve this question is obviously, let's actually get the combined array. So let's call this combined, and we can get this array in linear time of n plus m. How this is like a pretty pattern, very pattern of these lead code and GFG problems that to combine two sorted array. How do you do this? You keep two pointers, one on the array A, one on the array B, because we know that these both of these arrays are sorted, right? So what would be the minimum of the because see, in the combined array, the first value would be the minimum of A and B. The second value would be the second minimum of all the values in A and B, right? Because this would also be sorted. So what would be the actual minimum between these two values? The actual minimum between array A and array B would be the minimum of A, comma, or the minimum of B. So we do a comparison between these two pointers. Because this one is smaller, we add it first. Then because we have already picked it, then we move it here. Then the second minimum could be this value or this value. I think everyone knows how to solve this problem. Yeah, so if you were to use this solution, the time complexity that you would get is O of n plus n, because you are creating the sorted array and then returning the kth index or k minus 1th index to get the kth value, right? So this is linear time. Now, linear time would not give you TLE here because the constraints, if we look at the constraints here, yeah, the constraints are that n and m being the array size is 10 raised to power 6, so n plus m would also be of the scale 10 raised to power 6. So TL is fine, but is this the best optimal solution? No, this is not the best optimal solution. This is not the best optimal solution, because if we look at the expected time complexity, we can see that the expected time complexity is not linear. We need a logarithmic time complexity. So, okay, sorry. Where was this here? So how can we solve this on log n time? So obviously I gave you the hint of using binary search, but binary search on what? Binary search on answer doesn't make much sense here to use binary search on answer. And even if you were to do binary search on answer, the time complexity you would get is then log square n. Log square n is why. Because see, if we were to do binary search on answer, we'll do binary search on all the values on a array, like this value. Let's say we for searching for this value 3, like is this the answer, then we'll see how many values are less than it in A or how many values are less than it in B. So to get the number of values that are less than it in A is pretty simple, because see, if yeah, why is it pretty simple? Because if it is at index 1, then the number of values then that is less than this index is the index of it, right? But number of values that are less than on B is that for that you will have to find the lower bound of it, right? Or rather the upper bound of it, because every value, yeah, the upper bound of the value, the answer, so what we do in binary search on answer, if you did not know, is we basically binary search on the answer. It's pretty simple, pretty explanatory from the name, that this is the that what is this the answer. If this is not the answer, is because we now need the kth value, right? So if we do binary search on answer and then for some value, let's say x, we find that this is the let's say we want the 10th value, and we find for this x we get the 7th value. Then we know that okay, this is a 7th value, so we answer would not be less than x, it has to be greater than x. So we'll basically do that in because in binary search we keep two pointers, right, l and r. So we'll do that, l equals to x plus 1, the answer must be this. Or in the second case, if x is, let's say, 12, then we know that okay, this is the 12th value, so we need to the x value would be less than this, right? So by this is binary search on answer, pretty a short introduction to it. So uh, why would this be log square n? Because see, the number of values for this like x here, so let's say x was 3, so would be the index of this in this array, and then you will have to use upper bound to get the number of values that is less than from it. So from n, we were able to get to log square n, and log square n is pretty good. But can we do better? We can even get to log n. How we can get to log n is C. The idea is same. We will do binary search on answer kind of, but rather than doing binary search on answer, we'll do binary search on indexes of the array. So what I'm saying is I will search on binary search on this. So the array of indices are 0, 1, 2, 3, 4. So 0 to 4, you will search on this, like, and then again based on the value I get, I will get the value for the mid. If this is greater than k, then I will search on the left part. If it is less than sorry, if it is less than k, then I will search on the right part. If it is greater than k, I will search on the mid part. Basically I will find the mid. So I will search on, let's say, so I am saying that let's say a size is n, B size is M, right? So I will search on A. Let's say if I will search on array A. I will search for these indexes 0 to n minus 1. I get my mid. This is my binary search pattern that I am going to use. I get my mid pointer, right? Right. So earlier what we were doing is that let's say the x is A mid. The at this mid index, what is the value? Then I find how many of values in this B array is also less than equal to x, right? And then if that value is less than k or greater than k, on basis of that I am changing my lnr. But we can optimize this because see, this lookup on B is giving you a time complexity, because you are again for each binaries for each m or for each midpoint, you are again doing a binary search on m, so that is why you are getting a log square n complexity. How you can optimize this? See, we know that this x as at mid index, can we know that in the combined index this has to be at k minus 1th index, right? Because it is the kth value, so it has to be k minus 1th index. Can we know that? See, let's use this case of 23679, 23679 and 14810, 14810. So 0, 1, 2, 3, 4 and 0, 1, 2, 3. So let's see for 6. So 6 is at second index. So there are two values that are less than this in array A. Now for it to be the fourth value, the, the index has to be k minus 1. Now we can say that there has to be three values that are less than equal to this 6 value, right? So I already know that two values are less than this in array A. So how many values has to be less than it in B? Obviously one value, or we can say that k minus 1 minus the mid, right? Mid being the index on A. Okay. So that would come up to be 1 here. So I know that the value should be then. So now in B, this A mid, or I can say I'm referring X as A mid here. So let us say this value is some rec or a required thing kind of. Then can I say that X has to be between B rec and B rec minus 1? B rec and B rec minus 1. If X is in between this two, then X would be the kth value. Which makes sense, right? Because see, it should be, I think, greater. Okay, so yeah, I'm off by one here. It should be B rec because we need uh, yeah, it should be this b rec plus 1. I think this should be the case. Give me 1 second, I will confirm. So I struggle with this like off by one thing, but yeah, the condition should be that x should be between this b rec. Because see, I want this the number of values less than uh, this in b should be this value, right? K minus rec value basically. So like here we saw that we need one value less than this. So for one value less than this, yeah. So for one value less than this, then uh, basically one should be less than this. So the condition is that x should be between b rec minus 1 to b rec. If this is the case, then x is the answer. And if this is not the case, then either x would be like greater than b rec. If x is greater than b rec, then obviously we will do that r equals to mid minus 1. And else x is like less than b rec minus 1, then we'll do l equals to mid plus 1, right? So yeah, this is the idea of the question. You should try to implement this. I will show you my implementation, but there are better implementations to this. Like I was seeing the GFG's editorial and their implementation was a bit better. Let me show you my implementation, how I implemented it. So I am doing two binary search. One first binary search is basically over the elements on of array A, and I because see the kth element would either be from array A or it could be from array B. So first thing that I'm doing is see I'm searching for the array elements A if because see the question the case could happen that like here where is this so 6, right? So I'm searching for the elements from this array, but the fifth element is from this array, right? So here, as we can see, for from B, I'm getting my first value, I'm getting my fourth value, and then I'm getting my A. This is 1, 2, 3, 4, 5, 6. Then I'm getting my seventh value, right? So all the values in between are from A array. So that is why yeah, that could be happening. That is okay. So the GFG's editorial summation or the code was better because they did not do two binary searches. They only did one binary search. You can look up their code also. But yeah, I will show you my code. So first I'm searching on the values on array A. And if I'm getting answer is minus one is basically that this array A does not contain the kth value. Then I will just do the reverse of this. I will search on array elements B using A, and then I will return that. So yeah, if answer is not equals to -1, that is I got my answer. I will just return it. And this is pretty simple. Now let's see the search function. So in the search function, yeah, I'm just storing in n the size of A, B in M the size of B, and see the why I am doing this is basically what is the indexes that I need to binary search on. So I need to search on basically what we see is I need to search on array A. Now array A would have indices from 0 to n minus 1. Now could any index of this be the kth value? No, obviously not. Because see, if k is very small, let's say 1, so only the elements from 0 to 1 could be the kth element, right? How could second be the kth element if in this only it is the third element, right? How could second element be the kth element, right? And similarly, if k is very big, if k is very big, like let's say the array size is 5, so 0, 1, 2, 3, 4, this is the indexes, and array size is 10, then I need my b elements, right? Let's say b is of size 15, so I need some elements from b, then only I will get this, right? So that is why what we are doing is we are basically setting L to the minimum value that could be the kth element and R to be the maximum index that could be the kth element. Right, then I do my binary search on it. I get my mid value. I store this in X as we discussed, and I calculate this rec. So rec is basically the yeah the required index on B array. Right. So I store in LB and UB because the case could happen is that rec becomes 0. So if rec is 0, my lower bound becomes like because see we want this case, right? We saw where is it? Yeah, this case. But what if the required becomes 0? Then obviously b of -1 would give you a segmentation fault. So just to handle it, let's set the lower bound. Basically, the lower bound on this condition to be int minimum, right? any value is fine because the array has finished. And similarly, if required becomes m, if that is the b rec would give a segmentation world, I will set upper bound to int maximum, right? So that is what I'm doing here. Hopefully you are able to understand. So I initialize this both to int min and int maximum. If these are valid indexes, I store them into LB and UB. Then I just see if the x is in between this range. If it is the case, then I have got my answer. I will return x. If x is not in this range, so I need to have a bigger value. So that is why I will increment. I will set my scope of my search to L equals to mid plus 1, else I will set it to R equals to mid minus 1. And finally, if we were never able to get the kth value, I will return minus 1 because the kth element is in the B array, not in the A array. So this works. The time complexity is of log n, and we are not using any space. Hopefully you were able to understand how we are implementing this. Thank you for watching. Give me a like and subscribe, all of those things. Bye.